We continue with meteorite recovery in a totally different way. Hadrien, please. Thank you.
All right. Thank you for giving me the opportunity to talk. So today I'm going to be talking about the work from a PhD student within the Desert Fireball Network. His name is Seamus Anderson. He's now finished his PhD, moved on. But I think his work hasn't been presented to this community before, so I thought it'd be a good thing to do now. So many of you, I'm guessing, who've looked for meteorites, you spend half a day, spend a day, and at least me personally, I start thinking surely there's a better way of doing this. So I tried to do a bit of literature research about when, for the first time, people started thinking about, could we use drones for finding meteorites? It's probably as old as we started getting small drones, kind of affordable. But yeah, surely this is a good idea. And that was Seamus's PhD project, at least part of it. Oops, skipping ahead. So yeah, Seamus has been developing this whole system from collecting drone images, and then obviously the hardest part is identifying the images. So when we got all of that more or less ready, I gave him a challenge. We in Australia we had actually fairly badly observed fall. So only 2 cameras. The furthest one away was more than 400 kilometers, and the dynamics were not very good on it. So I was like, there it is. Here's 5 square kilometers to search. So there's probably 100-ish gram meteorite in there. Go find it. That's your challenge. Well, long story short, I'll skip to the end. So he found it. He found a small meteorite about this big in 5 square kilometers. So I was extremely impressed. I thought my challenge was really difficult, but he made it work, which is impressive. So how did he do it? So the easy part is obviously you need to take pictures of the ground at good enough resolution, so you can really resolve the meteorite and get typically around maybe 50 pixels across the sample you're looking at. So for this we use those DJI Mavic M300 drones. So we can fly. So we got pretty good cameras, so we can fly quite high and get good data. So yeah, typically cover a search area in 3 to 5 days. With that camera flying at 20 meters altitude, sampling at 1.8 millimeters per pixel ground resolution, and that generates about 300 gigabytes worth of data per square kilometer covered. So that's the big challenge when you're in the desert, is you need to process all that data. Collecting is the easy part. Processing it to identify meteorite samples, that's the hard bit. So that's what a typical survey looks like. That was quite a small one, I think about a square kilometer, and there's 15,000 images in there. So you got to process all of that. So the way we process it is we also capture some training data. So we put either real meteorites or spray painted rocks that could be, that human could definitely get confused into thinking it was a meteorite. Put them out there, put them on the ground, we get somebody to point to it, and then take a drone picture of it. I think Seamus tried photoshopping, but it basically doesn't work, doesn't look real enough. We also capture some background images from an area we're fairly confident there's no meteorite, so we can basically tell the machine learning algorithm down the track what the general background looks like. There's lots of false positives that it needs to be aware of, types of bushes you encounter in area, types of just background rocks, etc. And then the way you actually do that is you actually use machine learning algorithms. So Seamus, the way he did it was doing image classification. So I cut the image up in lots of little tiles, and basically ask, after doing some training, ask if is there a meteorite in there or not. The modern approach is actually to use object detection. So the YOLO models. YOLO stands for you only look once. So it does a detection and classification at the same time. It seems to be doing a pretty good job there. And we basically apply that to meteorites, and hopefully the machine learning can tell us like where the meteorites are in those images. Obviously, we get lots of false positives. I mean, so when you're training a machine learning model, you're always kind of trying to balance number of like real, basically not missing any, not taking the chance of missing the meteorite, especially if you only got like a couple in your survey area. You definitely don't want to be missing it. But trade-off on that is you get lots of false positives. So in typical foresight, that's kind of like what we would get on the order of like 100,000 false positives. So Seamus, for that, he developed a quick kind of like sorting like graphical user interface where you can select meteorite. Most of them you can like basically tell them apart and they say meteorite, not meteorite. So that gets rid of about a factor of 100. And then the next step is to look maybe a bit deeper into the image. So as you can see on the left here, you only got like the detection kind of center on the meteorite. You try to get some context about what else is in that area, which is useful to, I guess, reduce the number of candidates by another order of magnitude. And then the last two stages is you try to send a follow-up drone to get a closer look. And the last stage is you still think it's a meteorite. Yeah, you send actual people out there to go check it out. So yeah, you're basically trying to get rid of at least an order of magnitude of candidates of like false positives at each step. So you don't have to spend too much time like following up on foot. So there you go. Yeah, Seamus, yeah, made it happen. Still really amazed by that. So next step from that is it's us to do kind of a bit of a software improvement project. Again, they're still very impressed. To make this kind of like scalable. So like we want to take that to all the meteorites we've seen like 4 in Australia. There's still lots to find, lots we haven't searched. We want to make that really scalable and usable by people who maybe not that technically minded. That's another one we find in a completely different environment. As you can see here, like meteorite is right in the middle, but there's lots of other rocks that like color is not too dissimilar, and in that sort of terrain, the algorithm was really struggling to pick out the meteorites from the normal background rocks. So yeah, software improvement projects is, well, first here we want to limit number of things that can go wrong. Again, it's a really big data challenge. You got like a terabyte of data to process like in the field. You want to do it live. Ideally, at the end of the trip, you want to come back to the meteorites. You don't want to be spending too much time out there. So one thing we found is actually doing high performance computing in the field is quite difficult. And the approach we're taking is actually uploading our survey data back to a, I guess, central server or data center via Starlink. And that seems to be working pretty well. And if we go into connection, thanks to Starlink, is we can also, I guess, get more help reviewing the candidates from other people who might be like sitting in the office in a nice environment instead of us in the desert. And then we just want make the entire thing just easily controllable from a web app. I'm not going to go too much detail, but it's massive like software stack that we currently finishing the development of. And lots of bits, lots of bits to think about there. So I guess as a summary, like drone meteorite searching with machine learning, I mean that works. Like the gain at least for us is an order of magnitude. It's actually a bit more than that, more like a factor of like 15 on the time cost to recover a particular meteorite. We probably typically spend maybe like 2 or 3 days just surveying, like maybe 3 days on site to cover everything and process the data. And the smallest detectable meteorite is about 2 centimeters in diameter. Future direction for us. So I mentioned software improvement projects that hopefully will let us like hit a lot more sites, a lot more meteorites that we've seen. And it's going to make that process a lot more efficient. Then we want to try that on different terrains. So we've kind of been going to the same patch of, I guess, South Australia, where the background looks quite similar. But I think there's no reason that it shouldn't work in other areas. I'm thinking like planted fields. As long as not too many like black rocks around, I think it should be like very, very possible to take it to other terrains. So at this stage, we're not planning on open sourcing this, but we're very much like open to collaboration. Could definitely think about a way where other people collect drone images and they could process it basically using our software stack, I guess, installed on our data center. Definitely open to that. Right, thank you very much.
Thanks a lot for this most interesting talk. I guess there are several questions. Yeah, sure. Go ahead.
Very cool work. So you mentioned there that the smallest identified meteorite was 2 centimeters. Is that what's the percentage of accuracy on that 2 centimeters, or is just it sees it as a meteorite? That's the pixel scale from that height.
So at the small scale, you're obviously limited by your survey resolution, but yeah, I mean the algorithm like will detect larger things as well. Was that your question? Or
No, you mentioned that the smallest detected meteorite was 2 centimeters. Is that the resolution of the height you're usually scanning at?
Yeah. So that's limited by resolution. Yeah. In our particular case in Australia, going lower, obviously you'd think you just like fly lower, get more images, more data, blah blah blah. But we kind of limited by something else called like kangaroo poo. Like you start getting to that size range, that looks very black. It looks like very meteorite-like. Right. So.
Cool.
So when you fly over the whole field, is there an influence on the sun height? Like, do you scan it at local noon? Does it make a difference?
So a typical flight time for us in the summer, I think is 6 or 7 hours a day. That's something that's on my to-do list, is like have a look at when the number for spotters starts like skyrocketing because of like low solar elevations. But that's definitely a big factor. Yeah, we cannot fly kind of like all the time.
When somebody is wondering here if you can replace the drone by a herd of dogs.
One question in the back, and then we have to proceed.
In calibration, you use only black meteorites in machine learning, or other colors?
Now we just use black, obviously either real meteorites or fake meteorites. So that's when I saw the picture of Rebecca, I was terrified. It's like we're never going to find this.
So
I think where we search for meteorites, a lot of rocks that would be similar color, like similar texture. I think we probably won't be like finding Albrights anytime soon with this technique.
Okay, thank you.
Thank you very much again.